Welcome to lesson 4.2, Preparing Your Training Data. Overview, Overview. Your model is loaded and ready. Now comes the work that actually determines whether your fine-tuned model is useful or not. Preparing the data it learns from. This lesson walks you through loading the dataset you built in Module 3, applying the correct chat template, analyzing your token lengths, and configuring everything to run efficiently on your Tesla P40 GPUs. Budget about 30 minutes for this one. It's intermediate level work, but by the end you'll have a clean, validated training pipeline ready to go. Learning objectives. By the end of this lesson, you'll know how to load your Module 3 datasets, format them with the correct chat template, split them into training and validation sets, analyze token lengths to choose the right batch size, handle sequences that are too long, and build data loaders that feed your model efficiently during training. These aren't just setup steps. Each one directly affects how well your model learns. Loading your dataset. From Module 3, you should have two files sitting in your datasets folder, my_project_train.jsonl and my_project_validation.jsonl. If those files are there, here the load_dataset function from the Hugging Face datasets library reads both JSONL files into memory. Notice that both calls specify the train split, even for the validation file. That's just how the library works when you load local files directly. It doesn't infer a split from the file man, so you always get back a train split regardless. Don't let that naming confuse you. After loading, the code prints the example counts and column names. What you're looking for is 120 training examples, 30 validation examples, and a single column called messages. If those numbers match your Module 3 output and the column is named correctly, your data is loaded and structured exactly as expected. This prints the very first example from your training dataset. It's a quick sanity check. Before you run any transformations, you want to confirm with your own eyes that the data looks right. What you should see is a list of message dictionaries, each with a role key and a content key. If the structure looks garbled or the content is empty, catch that now rather than 3 hours into a training run. Here's what a well-formed training example looks like. 3 messages. A system message that tells the assistant its job, extract information and return it as JSON. A user message with the raw input and an ARM message containing the expected JSON output. This 3-part structure is exactly what the Llama 3.1 chat template is designed for. The model learns by seeing thousands of these examples. Input comes in, structured output goes out. The cleaner and more consistent your examples, the sharper your fine-tuned model will be. Formatting with chat templates. We'll mend the chat templates. You'll master these techniques quickly. Raw message dictionaries aren't what the model sees during training. The model expects a single formatted string where each turn is wrapped in special tokens that signal who's speaking and where each turn ends. That's what the chat template does. The get_chat_template function from Unsloth configures your tokenizer with the tokens measures units llama decimal integer part 3 fractional part 1 preserve order true. 2 flags matter here. Tokenize is false because you want the formatted text string, not token IDs yet. That happens later. And add_generation_prompt is false because you're formatting complete examples for training, not prompting the model to generate a continuation. The map call applies this to every example in both datasets. After it runs, each example's text field contains a properly formatted string with all the special tokens in the right places. The output preview confirms this worked. You'll see the tokens measure units llama decimal integer part 3 fractional part 1 preserve order true or special. The formatted output starts with the begin of text token, followed by the system header tokens. the system message content, and then the end of turn token. This sequence isn't arbitrary. It's the exact delimiter pattern Llama 3.1 was trained on. When your fine-tuned model sees these tokens at inference time, it knows precisely how to parse the conversation structure. If these tokens are missing or malformed, the model won't generalize correctly, no matter how good your training data is. Token length analysis. Before you set a single training hyperparameter, you need to know how long your examples actually are in tokens. This matters for two reasons. The model has a hard limit on sequence length, and token length directly determines how much GPU memory each example consumes, which determines what batch size you can use. The analyze_token_length function iterates through your dataset, encodes each example's text into tokens, and records the lengths. It then reports the total count, average, minimum, and maximum lengths. The critical check is whether any examples exceed 2048 tokens. If they do, the function warns you. Those examples will get truncated during training, which can silently corrupt your training signal. Better to know now and decide consciously whether to truncate or filter them out. The output shows 120 training examples with an average of 245 tokens, a minimum of 85, and a maximum of 520. The important line is the confirmation that all examples fit within the 2048 token limit. With a max of 520 tokens, you have plenty of headroom. This dataset is well within range, and you won't lose any training signal to truncation. These numbers also tell you which row of the batch size table to target, which you'll see in a moment. Handling long sequences. 1UK Illy-square sequences. 1UK sequences Zeker sequences. When you do have examples that exceed the model's context window, format underscore with underscore truncation gives you a controlled way to handle them. The function applies the chat template to format each conversation, tokenizes the result, and if the token count exceeds max underscore length defaulted to 2048, it slices the token list down to fit, then decodes it back to text. The model never sees a sequence longer than it can handle. The important caveat: truncation cuts from the end. For a conversation, that means the assistant's response. The part you're actually training the model to produce might get cut off. That's why the better approach, when possible, is to filter out overlong examples back in Module 3 before they ever reach this stage. Use truncation as a safety net, not a first resort. The right time to truncate depends on your task. For summarization or code examples, truncation often destroys meaning. For long multi-turn conversations, cutting off the end removes the assistant's response entirely. In most cases, the cleanest solution is filtering during data preparation in Module 3, so every example that reaches training is already within bounds. Keep that principle in mind as you build future datasets. Batch size optimization. Batch size is the number of training examples your GPU processes in one forward and backward pass. Larger batches train faster and produce more stable gradient estimates, but they consume more memory. Smaller batches use less memory but slow things down. On hardware with a fixed memory budget like your 24 GB Tesla P40S, finding the right batch size is a real constraint, not just a tuning knob. For Llama-3.2-3b-instruct running in 4-bit quantization, here's how token length maps to practical batch sizes and memory usage on your P40S. With examples averaging 100 to 200 tokens, you can run batch sizes of 8 to 16 and expect roughly 12 to 16 GB of memory usage. At 200 to 500 tokens, which is right where your dataset sits at an average of 245. Target batch sizes of 4 to 8 with memory usage between 14 and 18 GBs. Longer sequences compress your options further. 500 to 1000 tokens means batch sizes of 2 to 4, and 1000 to 2000 tokens drops you to 1 or 2. The rule of thumb: start at batch size 4 and increase only if your GPU memory stays comfortably below its ceiling. Here's a common situation you'll hit. Batch size 1 trains too slowly to be practical, but batch size 8 causes an out-of-memory error. Gradient accumulation is the solution. Instead of processing 8 examples in one pass, you process 2 examples at a time across 4 consecutive passes, accumulating the gradients before applying the update. The math works out identically. Your model sees the same effective batch of 8, but your peak memory usage stays at the 2 example level. This is exactly what these 2 parameters express. Per_device_train_batch_size of 2 means each forward pass processes 2 examples. Gradient_accumulation_steps of 4 means you multiply them together and your effective batch size is 8. You get the training stability of a large batch without the memory footprint. This combination is one of the most useful tricks in practical fine-tuning, especially on fixed memory hardware. Creating the final dataset. This block wires everything together into the SFT trainer from the TRL library, the component that will actually run your training loop. The training arguments object captures all the key decisions. Per_device_train_batch_size of 4 with gradient_accumulation_steps of 2 gives an effective batch size of 8. The learning rate is 2E4. The optimizer is Adama_8-bit, which reduces memory usage compared to standard Adama BLEU by storing optimizer states in 8-bit precision. The FP16 and BF16 flags are set automatically based on what your hardware supports. Your P40S support FP16 but not BF16, so FP16 will activate. The SFT trainer is then instantiated with your model, tokenizer, training arguments, and both datasets. When you see the success confirmation, it means the trainer has validated your configuration and is ready to train. Nothing runs yet. That happens in the next lesson. This block shows the lower level alternative, manually tokenizing your dataset and using data collator for language modeling to handle batching. The MLM false flag is critical here. It tells the collator you're doing causal language modeling, where the model predicts the next token, not masked language modeling where it predicts hidden tokens. Those are fundamentally different training objectives. The tokenize_ function encodes each example's text, truncates at 2048 tokens, and pads shorter sequences to uniform length so they can be stacked into batches. The map call applies this to both datasets and drops the original text column, leaving you with clean numeric tensors. This approach gives you finer control over the tokenization pipeline, but for this course you'll use method 1, the SFT trainer path, because Ansloff's integration handles several optimizations automatically that you'd otherwise need to configure manually. For everything in this module, use the SFT trainer approach. It's the path Ansloff is optimized for, and it handles the details of chat template integration, response masking, and efficient packing automatically. The manual tokenization path is worth understanding conceptually, but the SFT trainer is what you'll run. Save prepared dataset. Once your datasets are formatted and validated, save them to disk. The save_to_disk method serializes the entire Hugging Face dataset object, including the schema, the formatted text, and any metadata, into a directory you can reload instantly later. This matters because the formatting step takes time, and you don't want to repeat it every time you experiment with training hyperparameters. The load_from_disk call later brings the datasets back exactly as you left them with no reformatting required. When the success message appears, treat it as a checkpoint. Your preparation work is preserved and your training pipeline can pick up from here cleanly on any future run. Verify data is correct. The validate underscore prepared underscore data function is your final quality gate before training begins. It runs 5 checks in sequence. First, it confirms the dataset isn't empty. An empty dataset causes a cryptic training failure that's annoying to debug. Second, it verifies the text column exists, since that's what the trainer will read. Third, it tokenizes the first few examples and confirms the tokenizer processes them without errors. Fourth, it computes the average token length across the first 100 examples and flags anything unusually short, which might indicate empty or malformed examples, or unusually long, which could cause memory issues. Fifth, it scans for the special tokens that prove the chat template was applied correctly. Run this on both your training and validation datasets before you touch the trainer. A clean pass here means you can start training with confidence. A failure here is a gift. It's far cheaper to fix a data issue now than to discover it after a multi-hour training run produces a broken model. Complete data preparation script. This is the full end-to-end preparation script saved as notebooks/03-first-training/02-prepare-data.ipnb. It pulls together every step from this lesson into a single reproducible notebook. The model loads with the datasets load from your Module 3 JSON-L files, and the example counts confirm you have the data you expect. The chat template gets applied, token lengths get analyzed, and the prepared datasets get saved to disk. The final validation check confirms the datasets are non-empty and correctly structured. Running this notebook top to bottom should complete without errors and leave you with saved, validated datasets ready for the training configuration lesson. Common issues. The most common error at the formatting step is a dequar on messages. It means your dataset doesn't have a column by that name. Before assuming your data is broken, check what columns actually exist. Printing dataset.column_names tells you exactly what the library sees. If you get text or conversation or input instead of messages, that's not a data problem, it's a column name mismatch. Either rename the column during loading or update your formatting function to reference the correct name. 2 minutes to check this saves you from chasing a phantom bug. If training throws an error about sequence length, some of your examples are longer than max_seq_length. The fix is to filter them out before they reach the trainer. This filter call keeps only the examples where the tokenized text stays within 2048 tokens. The lambda encodes each example's text and checks the length against the limit. What comes out is a filtered dataset containing only examples the model can process without truncation. Run this after formatting and before saving. It's a one-liner that prevents a whole class of training errors. If your dataset is large enough to cause RAM pressure during loading, the solution is streaming. Load examples one at a time rather than all at once. Setting streaming =true on load _dataset changes how data is accessed entirely. Instead of reading the entire file into memory up front, it returns an irritable that yields examples on. You won't get a dataset object with a fixed length, but you also won't hit memory limits on large files. This is the right approach for datasets in the tens of thousands of examples or larger. For the 150 example dataset from Module 3, you don't need it, but keep it in your toolkit for when you scale up. Data preparation checklist. Work through this checklist before moving to the training configuration lesson. Confirm your training and validation datasets have the expected number of examples. Verify the chat template was applied and the llama special tokens appear in the formatted text. Check for empty or null values. Confirm your average token length and maximum token length are both within the 2048 token limit. Validate that tokenization works and that the encoded tokens decode back to readable text, a round-trip check that catches encoding issues, and confirm your prepared datasets are safe to disk. Every item on this list corresponds to a real failure mode. A clean checklist means you're ready for lesson 4.3, hands-on exercise. Here's your practical exercise for this lesson. Load the dataset you created in Module 3. Apply the Llama 3.1 chat template. Run the token length analysis. Validate data quality with the validation function. And save the prepared datasets to disk. Then report 3 numbers: total example count, average token length, and maximum token length. When you run this successfully, you should see formatted train and validation datasets, a token statistics summary, and a validation passed confirmation. Those 3 outputs together mean your data pipeline is solid and you're ready to configure training. Key takeaways: 7 things to carry forward from this lesson. Load your data from the Module 3 JSON-L files. Don't regenerate it. Apply the chat template. Skipping this step produces a model that doesn't understand conversation structure. Analyze token lengths before setting any hyperparameters. Start with a conservative batch size and increase only if memory allows. Use gradient accumulation to achieve large, effective batch sizes without large memory footprints. Run the validation function before training. Catching data issues early costs minutes, not hours. And save your prepared datasets so you can iterate on training configuration without redoing the preparation work. What's next? Your data is prepared, validated, and saved. The next step is deciding how the model actually learns from it. Learning rates, warm-up schedules, LoRa rank, and the rest of the training configuration. That's lesson 4.3, configuring training parameters. Additional resources. For deeper reading, the Hugging Face datasets documentation covers every loading and processing option available. The SFT trainer docs explain all the parameters you can pass to control training behavior. And the data collators documentation is worth reading if you want to understand what's happening under the hood when examples get batched together. That wraps up lesson 4.2. The tokenization pipeline transforms raw text into something a GPU can actually compute on. It starts with your formatted chat template string and passes it through the tokenizers encode function, converting human readable text into a sequence of integer token IDs. Those IDs are then truncated or padded to a fixed length defined by max_seq_len. So every example in a batch has identical dimensions, a requirement for the matrix operations happening inside the model. An attention mask accompanies each sequence, marking which positions contain real tokens with a 1 and which are padding with a 0, so the model doesn't waste computation attending to filler. For causal language modeling, the labels are shifted by 1 position relative to the inputs. The model's job at each position is to predict the next token, so the target at position n is the input at position n plus 1. Finally, the DALO-layer groups processed examples into batches and moves them to the GPU via CUDA. Understanding this pipeline end-to-end means you can debug any step when something goes wrong. There are 3 strategies for handling variable length sequences in a batch. Right padding appends padding tokens to the end of shorter sequences until everything reaches the same length. Simple to implement, but the padding tokens consume compute and memory. Left padding prepends tokens to the beginning instead, which can preserve positional encoding alignment for certain architectures. Packing is the most efficient approach. Instead of padding individual sequences, it stitches multiple short examples end-to-end into a single sequence up to the maximum length with a separator between them. This minimizes wasted tokens and maximizes the useful information per batch. Onslaught's SFT trainer supports packing natively. It's one of the reasons the SFT trainer path is recommended over manual tokenization for this course. These dataset statistics give you a clear picture of what your model will actually be learning from. The token length distribution centered around a mean of 236 tells you your examples are well within the 2048 token limit, and that your batch size calculations are based on realistic numbers. The instruction type breakdown, with extraction and summarization dominating, tells you where your model will be strongest after fine-tuning and where it might generalize less confidently. And the data source mix, with 40% from alpaca, tells you that a significant portion of your training signal comes from a single source. If that source has systematic biases or formatting quirks, your model will learn them. Use these statistics not just as a confirmation that data loaded correctly, but as a lens for understanding what your fine-tuned model will and won't be good at. The data loader flow connects your raw JSON-L dataset to the actual GPU tensors that drive training. The dataset enters the pipeline and gets formatted through apply_chat_template, which converts message dictionaries into properly tokenized strings. Those strings pass into data collator for seek-to-seek, which dynamically pads each batch to the length of its longest example, more efficient than padding everything to the global maximum. The torch dart loader then handles shuffling the dataset each epoch and grouping examples into batches of 4. What comes out the other end is a GPU tensor batch containing 3 arrays: input_eds with the token sequences, labels with the shifted targets for computing loss, and the attention mask. That batch goes directly into trainer.train.train_saw, which runs the forward pass, computes the loss, and updates the weights. Every step in this chain is necessary. A misconfiguration at any stage produces incorrect gradients or silent training failures. Attention masks are how the model distinguishes real content from padding. In sequence A, the tokens for hello and world carry attention mask values of 1. The model attends to them fully. The padding tokens at the end carry values of 0. The model ignores them during the attention computation. Sequence B follows the same pattern. Without this mask, the model would treat padding tokens as meaningful input and try to attend to them, which corrupts the attention scores and degrades training quality. When you use data collator for language modeling or data collator for SAC-to-SAC, the attention mask is generated automatically alongside your input IDs. But if you ever build a custom data pipeline, generating the mask correctly is the contrast between padding and packing comes down to how much of each batch contains useful information. With padding, every sequence is extended to match the longest example in the batch. If your longest example is 512 tokens and your shortest is 50, the short example wastes 462 token positions on padding, positions where the model computes attention scores that contribute nothing to learning. With packing, those short examples are concatenated together into a single sequence up to the maximum length, separated by end-of-sequence tokens. The same batch now contains far more real training signal and far fewer wasted computations. On fixed memory hardware like your P40S, packing effectively increases the amount of useful data you process per GPU hour, which translates directly into faster convergence. The batch construction pipeline moves your raw JSON-L data through a series of transformations before it reaches the GPU. First, the format function applies chat templates and converts message dictionaries into formatted strings. Next, the tokenizer converts those strings into integer token sequences. Sequences that exceed 2048 tokens get truncated at this stage. The dataset then gets shuffled with a fixed seed, 42 in this example, so results are reproducible across runs while still randomizing the order the model sees examples. The dayloader groups the shuffled tokenized examples into batches of 2 and yields them one batch at a time to the training loop. Each stage in this pipeline is deterministic given the same seed, which means you can reproduce any training run exactly by keeping the seed fixed. Response masking is what ensures your model learns to generate assistant responses, not to memorize the prompts that precede them. In a training example, the system message and user message are part of the input context. The model should read them but not be penalized for predicting them. The assistant response is what the model should learn to produce. Response masking sets the loss calculation to ignore all tokens in the system and user turns, marked here as masked, and only compute loss on the assistant tokens. This means gradient updates only flow from the part of the sequence the model is actually being trained to generate. Without response masking, the model wastes capacity trying to predict the system prompt word for word, which hurts both training efficiency and final model quality. Unsloth's SFT trainer applies response masking automatically when it detects the chart template format. This diagram shows the complete data preparation pipeline from raw shared GPT rows to a processed dataset ready for fine-tuning. The format underscore function applies chat templates to structure each conversation correctly. The tokenized function converts the formatted text into input underscore IDs and labels, the numeric arrays the model actually computes on. The mask underscore labels function then zeroes out loss contributions from the prompt tokens, leaving only the assistant response tokens to drive gradient updates. The truncate underscore sequences step enforces the 2048 token hard limit, cutting anything that exceeds it. The final output is a processed dataset where every example is formatted, tokenized, masked, and within bounds. Understanding each stage in this pipeline means you know exactly where to look when something in your training data produces unexpected model behavior. This graph shows how day loader worker count affects throughput and CPU utilization. Throughput climbs steeply as you add workers, roughly tripling by the time you reach 8 workers. CPU utilization rises more slowly and plateaus around 50% after 4 workers. The practical implication: there's a point of diminishing returns where adding more workers costs CPU resources without meaningfully improving data loading speed. For most setups, 4 workers hits the sweet spot. One Windows-specific note: set pin underscore memory to false in your date loader. On Linux, pin underscore memory equals sign true speeds up host to GPU transfers by keeping data in page-locked memory, but on Windows the implementation behaves differently and can actually slow things down or cause errors. Keep it false and you'll avoid that class or problem entirely.